Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last session, we have discussed about incomplete tension field beams. We have derived particular stress formulae, and as well as we have seen what is post-buckling behavior of the plates, and followed by one numerical we have seen in the last session. So in today's session, we are going to study about the unsymmetrical bending of beams. So it's very important to study of the unsymmetrical bending of the beams because the loads or the bending moments that we apply, so most of the time it's not going to be symmetric. So the unsymmetrical loads that we are going to apply, so because of that the beam bends in an unsymmetrical manner, and therefore it is very much important for us to find out the stresses associated with that, and in fact, to know the behavior of the plate when the unsymmetrical loads are occurred on the plate. So let's try to see what is the unsymmetrical behavior of the plates. And the learning outcomes in this module are the students are able to analyze unsymmetrical bending of the beams, and the students are able to determine the formula for direct stress distribution. In the last class, in the mechanics of solid subject, we have one formula that is equals to m by I equals to sigma by y equals to E by R. So usually we'll call this as bending equation or bending formula or engineer's theory of bending, and in which m is the bending moment, I is the moment of inertia, sigma is the direct stress due to bending, and y is the distance from neutral axis, E is the Young's modulus, and R is the radius of curvature. So in this, what you do is you'll consider these two, and then you'll write the formula that is sigma equals to m by I into y, and then depending upon the cross section, you'll find out the bending moment, and depending upon the beam and depending upon the cross section, you'll probably find out what is bending moment and what is moment of inertia and what is y, that is a distance from neutral axis, and you'll substitute here. You'll try to find out the direct stress, that is sigma, and sometimes you may also calculate the maximum stress also, for which you need the bending moment should be maximum. So, and in fact y is also should be maximum. So this is the bending condition which we have seen, which is nothing but the symmetrical bending. And there we don't consider mx or my or mz like that. So we just consider one small rectangular element, and we'll try to apply the bending moments of m of equal intensity on both the ends, so that the beam is going to bend, and then we assume that the top flanges are going to be compressed and the bottom layers are going to be tensile, that is tension in nature, and there exists a layer which about which there exists no tension or compression, and which we call it as neutral axis. So this is the symmetrical bending which we have seen in the previous mechanics of solid subjects. But moving on, for all the practical applications, we don't rely on the symmetrical bending, and usually so the bending moments are not going to be same on x plane and y plane. So now we are going to consider the two bending moments, that is mx and my. Okay, so which yields again the stresses sigma x and sigma y. So like that, we are going to see the unsymmetrical bending of the beams. So again, symmetrical bending, we have one glimpse of this slide. That is, a bending moment m is applied on the beam, that is plane sections remains plane, that is a assumption what we consider, and the beam is bent in a curved manner after applying bending moment of m, in which you can assume the r is the radius of curvature, and we got the relationship m by I equals to sigma by y equals to E by R, and in which I is the moment of inertia of the section, E is the Young's modulus, sigma is the bending stress, and y is the distance from neutral axis. And so why do we need to study the unsymmetrical bending? So for that, the aircraft, we know that it is an assembly of stiffened shell structures, so which consists of either single cell or multi-cell, and they may be open or closed section beams. So examples you can consider the single cell closed section fuselage or multi-cell wings, etc. So all these beams are usually they are subjected to bending, shear as well as torsional loads. And for example, if you look at this the sections, So you have thin walled channel section, and you have T section, Z section, I section, top hat sections. So these are the sections which we use for all these aircraft construction, and this we use as the beams. And then so these sections are usually stiffened the thin skins of cellular components, and they provide support for the internal loads from the floor and the engine mounts, etc. So these structural members are called as open section beams, while the cellular components are called as closed section beams. Okay, so the fundamental difference between the open section and closed section beam is nothing but, you can, for example, T section, you can consider this as open section. Z is also open section. I is also open section. Channel is also open section. Top hat is also open section. And what is a closed section is nothing but, it's a cellular component and it's complex group. So you may get a circular, or you may get a semicircle or ellipse. Okay, you may get a oval shape. Okay, so all these are nothing but the examples of the closed section beam. So the aircraft, you may have a components of open section, or you may have a components of closed section. Sometimes you may have a combination of both open and closed section beams with a single cell or multi cells that are mentioned. So symmetrical bending is a special case of bending of beams of arbitrary cross section. In fact, first we have the unsymmetrical bending of beams only, and from the unsymmetrical bending of the beam, the symmetrical bending, which is a special case, have been drawn by substituting mx equals to my equals to m. And the assumptions again, they are the similar assumptions, that is plane sections remain plane even after bending. Material of the beam is linearly elastic, homogeneous, and obeys Hooke's law. So unsymmetrical bending, and the procedure is the same that of symmetrical, but here we do for the arbitrary section rather than the symmetrical cross sections that we've seen in mechanics of solids. And later we will apply it for the thin walled open and closed section beams that are subjected to the bending moments, that is mx and my. So as I mentioned here, the bending moments mx and my we are going to use, and we assume mx is the bending moment applied in x plane, that is bending moment per unit length, and my also will consider the bending moment per unit length applied in y plane. So these are the two bending moments that we are considering here instead of m alone. So let us assume let us assume one arbitrary section that has been shown in this diagram. So understanding this diagram is very, very important. And so here we have, you can see arbitrary section that is taken like this, and the length is also taken like this, and xy axis system. So x axis is in this direction, y axis is in this direction, and z axis is in this direction. And then you can see the loads that are acting here. So P is the axial load that is acting, and you can see the other load, that is Sx is the shear load in acting parallel to x direction, and then Sy is the vertical shear load acting parallel to the y direction. And you can see the two bending moments mx and my, that is mx is applied on a plane parallel to x axis, and my is applied on a plane parallel to y axis. And let's try to apply the torque over here, which is we are applying on about z axis. And then we'll consider one small elemental strip here, and let us assume the that is distributed load as wx over here and wy over here. So this is a diagram which we have, and also you can consider the u, v, z, w are nothing but the displacement components in x, y and z directions respectively. So this is a diagram completely which we need to understand, because whatever the derivation we are going on, that is finding the direct stress distribution. So we'll write all the equations from this diagram only. So before we go into the actual derivation, there is a resolution of bending moments. If the angle is less than 90 degrees, so if you try to consider this m, so if the angle is less than 90 degrees, and you can see here, if the angle is with respect to the horizontal x axis, then the component, that is m, you get component onto this axis, and it is regarded as my, and which can be written as my equals to m into cos theta. Okay, similarly, when m is taken place onto y axis, that is parallel to y axis, So you're going to get mx and you're going to get m into sine theta. So this is a resolution of moment, just like resolution of force what you studied in the engineering mechanics. Okay, and that is for the angle which is less than 90 degrees. Second case, you can see the angle which is greater than 90 degrees, that is between 90 and 180. You can consider somewhere between 90 and 180, and if you try to apply bending moment m, it's going to give two components. One is parallel to x-axis and one is parallel to y-axis. So the component parallel to x-axis, which you can see here, that is m equals to, or mx equals to m into cos theta, and my equals to, you can get m into sine theta. So these are the components, moment components when the moment is applied between less than 90 degrees, somewhere between 0 and 90, and greater than 90 degrees, somewhere between 90 and 180. So you can see here, mx can be written as m into sine theta, and my equals to, you can write it as m into cos theta. So these are the two components that you can arise from the bending moment. So for theta that is less than pi by 2, mx and my both are positive, and for the angle theta that is greater than pi by 2, mx is considered as positive and my is considered as negative, as shown in the figure B. So coming to the direct stress distribution due to bending, and so we considered that arbitrary section, and now we are going to consider one small element in that arbitrary section, and let's try to have a diagram. So we are considering one small arbitrary section, side view you can take, and in which you're considering one small element strip, that is one small element. Let us assume the elemental area is delta A, and from, if you consider the axis system, that is origin, so let us assume that this small elemental strip is at a distance of x from y-axis and at a distance of y from x-axis, and let us assume a neutral axis that is passing through the x and y axis system, and in which you can consider the distance from the neutral axis to the origin is nothing but rho, that is considered, and also the distance from the neutral axis to the point element where we are considering, let us assume it as zeta. Okay, and similarly mx is the bending moment that is applied parallel to x-axis, and my is the bending moment per unit length applied parallel to y-axis, and the total area you can consider it as total, that is capital A, and elemental area you can consider it as delta A. So this is the first diagram which we have seen, and in the second diagram, and let us assume that the neutral axis coincides with the origin of the xy axis system. So when the neutral axis coincides with the origins, that is at C, then the zeta value is going to be increased, that is zeta value, and you can take from here to here, and rest of everything, all the diagram is same. And since this neutral axis is making an angle of with cx, that is horizontal axis cx, let us assume alpha as the angle that it will make with respect to cx as well as the neutral axis. Okay, so from this diagram, let's try to derive the formula for direct stress distribution. So the derivation is very simple. So first we are going to add the strains, that is either stress in x direction and stress in y direction, and let's try to write sigma x and sigma y, and then we elaborate it. Okay, so let's look into this one. So the beam support two types of bending moments, that is mx and my, and which bends about some axis in its cross section, which is therefore an axis of zero stress or a neutral axis. Let us suppose that the origin of the axis coincides with the centroid C of the section, and that the neutral axis is distance rho from C, and therefore the direct stress sigma z on any element of area delta A at any point xy, and which is the distance of zeta from the neutral axis, is given by sigma z equals to E into epsilon z. That is nothing but, we know that Young's modulus is nothing but stress by strain. So from that you can write stress in z direction, that is sigma z equals to E into epsilon z. So if the beam is bent to a radius of curvature rho about the neutral axis, by a comparison with symmetrical bending theory, and which we can write it as epsilon z, that is strain in z direction, can be written as zeta by rho. That is, usually we write strain as, nothing but change in length by original length. Okay, so we write like that. We write epsilon z equals to zeta by rho from the diagram. So once you know the stress, that is epsilon z, and you can calculate the stress, that is sigma z equals to Young's modulus into strain, and we write Young's modulus E into strain as zeta by rho from the above equation. And once you know the stress, the beam supports the pure bending moments, so that the resultant normal load on any section must be 0. So it's very, very important that the resultant normal load. So if sigma z is the stress of a small element, and it should be multiplied with the elemental area, that is sigma z into dA, so that the total arbitrary section, if you want to cover, so you can integrate it over area A, and this is nothing but the total resultant load, resultant normal load. Okay, so when you consider the concept of pure bending moments, the total resultant normal load must be 0. So therefore, equating that equation, that is equal to 0, and then the above expression, you can substitute sigma z, that is equals to Young's modulus into zeta by rho into this equation, and you can rewrite that equation, and you will get an expression, that is integral A zeta into dA equal to 0. And now from the diagram, we need to evaluate what is that zeta, and from the diagram you can see, from the geometry of the diagram, you can easily write out, that is zeta is nothing but x sin alpha plus y cos alpha, that you can get from the diagram, and then you can substitute for sigma z, and therefore sigma z equals to E by rho into z you have, and into zeta you have. In place of zeta, you can substitute x sin alpha into y cos alpha. So that is sigma z equals to E by rho into x sin alpha plus y cos alpha. So once you get this one, the next step is introducing the mx and my here. So mx, so this one is very, very important, and mx and my are the applied moments. So whenever you try to apply mx bending moment, it's going to induce the stress in x direction, and when you apply my bending moment, it is going to induce the stress in y direction. So therefore, if you try to write those stresses with respect to sigma z, and you can write mx is equals to sigma z is the stress multiplying by the area, and it's going to give force, and where y is the perpendicular distance. Okay, so stress into area, that is nothing but the force multiplied by the perpendicular distance, you are going to get moment. So therefore, we are taking over the integral A. So that is nothing but mx. So mx is equal to integral A sigma z into y dA. In the similar manner, the applied bending moment my can be written in terms of the stress, that is equal to integral A sigma z into x into dA. So once you get this formula for the applied bending moments mx and my, you can substitute for sigma z from the previous equation. And what is that previous equation? Sigma z equal to E by rho into x sin alpha plus y cos alpha. Now this complete equation we are going to take and substitute for mx and my by replacing the z. So when you do that, what you are going to get is, so when you try to substitute, let's try to substitute one value here. For example, mx equal to integral A. So sigma z, that you can write it as, E by rho into x sin alpha plus y cos alpha. Okay, that you can substitute here, and again there is left, what is left here, it is y into dA. Okay, so once you get this one, and now what you can write here, it is integral A first E by rho, you can take common and you can take it out, E by rho, and what you get here is x, you try to multiply this with this one, so you'll get xy into sin alpha plus y square into cos alpha into dA. This you are going to get. Okay, so further you can write this as E by rho integral over A and this you can write it as xy dA. You can write as xy dA into sin alpha plus y square dA into cos alpha, you can write. Okay, so when you try to take the integral form, so this integral, this especially if you look into this one, so you are going to get integral xy dA sin alpha, you can write it outside. And if you try look at into the second one, so you can write as integral y square dA, again you can write the cos alpha outside of it. Okay, so this is over A. And from the definition of the moment of inertia, integral y square dA can be written as the moment of inertia about x-axis, that is Ixx, which is shown here. Okay, similarly the product of inertia, that is xy into dA over the integral d, and you can write it as Ixy. So you can look at into this one. Similarly, another one is nothing but if you have integral x square dA divided integral x square dA over the area, this you can write it as Iyy. Okay, so with these changes, by writing Ixx, by writing whatever we are having here in terms of Ixx, Iyy and Ixy, and you can replace this all, you can write mx. You can write mx, that is equals to E sin alpha by rho into Ixy, that is the first term, plus E cos alpha by rho into Ixx, that is nothing but the second term, this one. Okay, so rewriting that. So similarly, we can rewrite the my as E sin alpha by rho into Iyy plus E cos alpha by rho into Ixy. Okay, so this is how we try to write, substitute for sigma z, and writing the results in terms of the moments of inertia, that's Ixx, Iyy and Ixy. So next what we are going to do here, it is we are trying to put it in the matrix form, that is mx and my, and it is very simple to put it in the matrix form, like you can write mx my in the matrix form here, and that is equals to, and that similarly what are constants and what are what you can take it out. For example, you can take from this equation E by rho, E by rho, E by rho, E by rho. So here you can take E by rho, you can take outside, and then you can write sin alpha and cos alpha, you can put it in the column matrix, and followed by another matrix in which you have Ixy, Ixx, Iyy, Ixy. So in this way you can write out the matrix form. If you multiply, you're going to get the same equations what you have. So mx my can be written as E by rho Ixy, Ixx, Iyy, Ixy into sin alpha cos alpha, and then further you can write it as E by rho into sin alpha cos alpha, you are keeping as it is, sending this 2 by 2 matrix, that is Ixy, Ixx, Iyy, Ixy to the other side of mx my, so that it will become inverse into mx into my. So this is a 2 by 2 matrix, this is the order of 2 by 2 matrix, and when you take inverse, you know that you're going to get adjoint A by determinant A, and we are writing that for the 2 by 2 matrix, and this is the adjoint A, that is minus Ixy, Ixx, Iyy minus Ixy divided by determinant A, Ixx, Iyy, Ixx, Iyy minus I square xy you are taking here, okay, into mx my. Okay, so this is nothing but what? E sin alpha. Now from this diagram what we are going to write here, it is, now from this diagram we are going to write what is E sin alpha by rho. E sin alpha by rho. Let's look into this one, E sin alpha by rho. So what is that E sin alpha by rho? That you can see here by multiplying first row with this column. So you are going to get mx into minus Ixy plus my into Ixx divided by Ixx, Iyy minus I square xy is you are going to get, that is E sin alpha by rho. Similarly, if you try to write E cos alpha by rho, the second one, and you have to multiply the second row with the column, and you are going to get another equation, that is E cos alpha by rho. E cos alpha by rho, that is equals to, and if you try to write, that is you're going to get Iyy into mx minus Ixy into my divided by Ixx Iyy minus I square xy. So this E cos alpha by rho, this is E sin alpha by rho. Now let's go back and see what is the formula for direct stress distribution sigma z. And if you look at it, go back and see, that is sigma z equals to E by rho x sin alpha plus y cos alpha. So here we are going to add this. So sigma z equals to E by rho sin alpha into x. I am writing separately. So E by rho cos alpha into y. Okay. So for E by rho sin alpha, for E by rho cos alpha, we have to substitute what we got in the previous expression, that is E cos alpha by rho, E sin alpha by rho. Substitute in the equation, you are going to get an equation like this. So what is that equation? Sigma z equals to my Ixx minus mx Ixy divided by Ixx Iyy minus I square xy into x plus mx Iyy minus my Ixy divided by Ixx Iyy minus I square xy into y. So this is the formula for the direct stress distribution due to unsymmetrical bending, and which we need to remember for the problems to solve. Okay. And further, if any assumptions are there, again it will reduce the form of the equation. That, for example, if you have at least one axis of symmetry, either Cx or Cy as axis of symmetry, we know that the product of inertia will become 0. You can substitute product of inertia becomes 0 here, and you left with the equation. When you substitute 0, Ixx will get cancelled in this, and in this Iyy gets cancelled, and you left with the equation for at least one axis of symmetry, that is mx by Ixx into y divided by my into my divided by Iyy into x. And for example, if any of either mx or my is 0, for example, if we assume my equal to 0, then you get sigma z equals to mx by Ixx into y, which is nothing but the symmetrical bending stress formula. If you try to remember, sigma equals to m by I into y. So this is symmetrical. So the symmetrical bending stress formula is derived from the unsymmetrical bending of beams. Okay. For example, if you try to substitute mx equal to 0, then you'll left with only my by Iyy into x. Okay. So that is a formula. So that is sigma z can have two forms depending upon the values of mx and my. Okay. And after that, we will try to define the neutral axis. That the neutral axis is given by tan alpha, that is equals to y by x. Okay, in which you can find the slope of the any equation. So y na by x na, that is equals to, so to find out this one neutral axis, position of neutral axis, the sigma z, it must be made equal to 0 for finding the direct stress. The total direct stress should be equal to 0, and from this you are going to get y na by x na, that is equals to minus my into Ixx minus mx into Ixy divided by mx into Iyy minus my into Ixy, and in which alpha is positive and xna and yna are of opposite sign. So that is nothing but what? Tan alpha. So tan alpha, the slope of the equation is equals to y by x, and tan alpha equals to, you can get this angle. So this is nothing but angle of inclination alpha, and that will determine the neutral axis position. That is alpha equals to some angle theta or whatever it is. So it will give you the position of neutral axis. Okay. So that's it from the today's class, and which we have seen unsymmetrical bending of beams rather than the symmetrical bending of the beams. So thank you for watching this session. In the next session, we are going to see some more problems corresponding to the direct stress distribution due to unsymmetrical bending. Thank you.